In this video, we're going to talk about some integration techniques, particularly integration by parts. So far, integrals are evaluated by either we have a specific formula for a specific function, or we use substitution method. But what about the integral of ln of x? So if we're going to start or try to start with it, we have the integral of ln of x dx. As far as we know, we don't have a function whose derivative is ln x. What we have is that the derivative of du over u, where u is a differentiable function of x, would be equal to ln of u plus c. But a derivative, but the integral of ln u, we don't have such formula for that. If we are to try the substitution method or the u sub method, we don't have much of a choice but to let u be equal to ln x. And if we do so, we're going to have du is equal to du over, that will become 1 over x. Which is kind of difficult to place there. So this is the reason why neither of these are options. So at this point, we do not have knowledge to do this integral. So if we face such integrals, maybe the next thing that we do is we have to do integration by parts. And we're going to start with integration by parts by the product rule. Let's clear this up. There. So the product rule, if you remember, the product rule for finding the derivative, if we have two functions, let's have let u and v be differentiable functions of x. Oops, sorry. There you go. So if we are to find the derivative of uv in terms of x, the derivative of v in terms of x, we know that the formula for this is the original first function times the derivative of the second function plus the derivative of the second function times the original second function. The derivative of the original first function times the original second function. So let me rewrite that. I'm going to have the derivative of uv is equal to u dv plus v dv. Now let's integrate this equation. Let's integrate both sides. And we know that if we do integrate this gets cancelled, so we simply get 2b. Integrating this, we're going to get the integral of 2dv plus the integral of v du. There. Now we just need to rewrite something so that it would be the formula for integration by parts. We transpose this here and then change this. So uv minus the integral of v du is the integral of u dv. Hence, the formula for integration by parts is that the integral of u dv is equal to uv minus the integral of v du. This is the formula for integration by parts. Some call it IBP, some just call it by parts. So, if you notice that we have actually two functions, one is the usual function and one is the derivative of another function, then we can separate them quote-unquote by parts and use this formula to evaluate its integral. Now, let's work with that with ln x. So, again, our formula, the integral of u dv is equal to uv minus the integral of v du. Which means we would need to assign what is u and find its du, assign its v, and its dv. So the given to us will be u and dv. And then from there, we would have to figure out what is du and then v. Now, it's up to you which one, not really up to you, but at first you have to be the one to determine which of which is u and dv. And as you know, the process of v to dv, that's finding the integral, while the process u to du is finding the derivative. So you have to remember that. In this specific case, since we're looking for the derivative of ln x dx, we cannot place ln x in dv because we do not know what is its integral. So we don't have much of a choice here but to place ln x u and to place dx in dv, because we know the integral of dx would be x and the derivative of ln x would be 1 over x. So there you go. Sorry, this should be 1 over x dx. We're doing integration there. Alright, so now that we've figured out our u, v, d, and dv, we now fill it in our formula. That the integral of ln x dx will be equal to, that's u times v, which is ln x times x, minus the integral of v x du, 1 over x dx. So this, we'll just rewrite this in a specific order so that it's not confusing. So we can write it as x ln x, while here we get it's cancelled integral of dx, which we will know was just simply be x. Hence, therefore, the integral of ln x dx would be x ln x minus x plus c. You might want to factor out that x, but you can also stick with this x. So let's have another example. Now we have integral of x squared e raised to x dx. So the first thing to do here is to determine which is our u, which is our dv, and then du and v will follow up. Again, the basic formula here, the integral of u dv is equal to uv minus integral of v du. So based from this, we all know that the integral of x squared and e raised to x are easy to get. The integral of x squared alone will become x cubed over 3, while the integral of e raised to x will more or less be just e raised to x. So since it's easier for the integral of e raised to x, it's simpler rather, but let's try that. So let's let dv be e raised to x dx, while u be equal to x squared. Because as we know, it would also be easier for the derivative. It's also easy for the derivative of e raised to x. But the integral of x squared is a little bit more complicated because of the fraction part. So let's try this pairing first. If we do this, then du will become 2x dx. With this, v will simply be e raised to x. So now following our formula, we're going to have x squared times e raised to x minus the integral of our v, which is e raised to x times du 2x dx. So rewriting this, we're going to simply have x squared e raised to x minus 2 integral of x e raised to x dx. Now at this point, we simply cannot just find the integral of x times e raised to x dx, because if we try to do u substitution, for example, if we let u be equal to e raised to x, du will be equal to e raised to x dx, but the x will not be found. So it looks like we have to do again integration by parts, because the integral needed in du cannot be still integrated by either substitution method or our integration formulas. So hence at this point, we are going to do again integration by parts. So again, it's easier if we let dv be equal to e raised to x. So therefore, I'm going to have u be equal to x and dv be equal to e raised to x dx. Hence, making du be equal to dx and v be equal to e raised to x. Hence, I'm going to have x squared times e raised to x minus 2 times, that's x times e raised to x minus the integral of e raised to x times du, which is dx. There you go. So now we know that this is now according to our formulas. So we're going to have x squared e raised to x minus 2 times x times e raised to x minus e raised to x. Then our plus c already so that we don't forget. All we need to do is to distribute this negative 2 here. So I'm going to have x squared e raised to x minus 2x e raised to x minus e raised to x plus c. You may already have this as answer, or if you would like, you can also factor out the e raised to x, making, therefore, integral of x squared e raised to x dx is equal to e raised to x times x squared minus 2x plus 1 plus c. So the key in this example is that we actually repeated our integration by parts. If in the first try you get an integral that is not integrable by either the substitution method or the basic integration formulas, then we might have to do integration by parts again, just like what we had in this example. So let's have another example. We now have integral of x times the inverse tangent of x. Pause the video and try to see if you'll be able to figure out what is the integral of this one. Assuming you have done so, the first thing to do is to again our formula, integral of u dv will be equal to uv minus integral of v du. So we have to select our u and our dv, and then later on our du and our v. Obviously, we don't have an integration formula that comes out as inverse tangent. So it would be easier for us to let the inverse tangent of x as our u and x dx as our dv. So with that in mind, the derivative of inverse tangent of x that we have, that becomes dx over 1 plus x squared. Sorry, let's write that a bit more properly. So that's dx over 1 plus x squared. And with x dx as our dv, our v becomes x squared over. So therefore, we have the integral of x inverse tangent of x dx is equal to the inverse tangent of x times x squared over 2 minus integral of x squared over 2 times dx over 1 plus x. So we'll simplify things. We can rewrite this as now, if we want 1/2 to stand out, it's alright to show that it is a constant. So we have 1/2 x squared inverse tangent of x minus, we factor out 1/2 in our integral, so it becomes integral of x squared dx over 1 plus x squared. We know that we cannot do substitution here because if we do substitution method, 2x will not come out. Both of the ones that we're going to differentiate if we're going to do u substitution is x squared. So therefore, we need to have 2x somewhere. But since we do not have, then we might not be able to easily have this formula. So So if you remember in our previous examples before, when we encounter a fraction, maybe it would be better to separate the fraction so that it's easier for us to do the integration. Although it's kind of difficult in this specific case because it's just a monomial in the numerator, maybe you can do the actual division. Because we know that if we perform the actual division, we're going to have a remainder as a separate term. So maybe we can try that. So from here, we're going to actually divide x squared by, that's 1 plus x squared, or let's rewrite it as x squared plus 1. You may perform the long division or you may perform the synthetic division. In this case, let's just perform the long division. It's easier on our end. So, we're going to have x squared divided by x squared plus 1. 1 times x squared times x squared, 1 times 1 plus 1. In subtracting, this becomes 0 and this becomes minus 1. This tells us that x squared over x squared plus 1, or 1 plus x squared, is equal to 1 minus 1 over x squared plus 1. And then let's try this. So we can now rewrite this as, let's just rewrite the first term, 1 half x squared in the standard of x minus 1 half times the integral now of 1 minus 1 over x squared plus 1 dx. So in doing so, we're going to have now 1 half, let's just rewrite again this part, minus 1 half. Now, if we do our distributions and all, this becomes minus 1 half times the integral of dx minus 1 half times the integral of dx over x squared plus 1. From here, we can now easily actually find our integrals because they do follow our integration formulas. So I'm just going to still have 1 half x squared inverse tangent of x here. This becomes the integral of dx is x, so this becomes minus 1 half x, and the integral of dx over x squared plus 1 is actually the inverse tangent of x here. So therefore, this becomes 1 half inverse tangent of x. Therefore, let's write it here, the integral of x inverse tangent of x dx is equal to 1 half x squared inverse tangent of x minus 1 half x minus 1 half inverse tangent of x plus c. But we don't forget that. There you go. Now let's try another example here. Pause the video and then try to see if you're going to if you will be able to apply integration by parts in evaluating this integral. Assuming you have tried, let's try to work this out here. So again, the integral of 2dv is equal to dt minus integral of dtu. So we need to select our u and our t to get our q, and so excuse me, sorry. In this case, it's kind of difficult to choose because, well, you find the integral, you can easily find the integral of both x squared and sine 10x. Although, you know, it's up, it might not work if you try which is which. Sorry. What I'm trying to say is that you have to choose carefully because sometimes the combinations might work, sometimes the combinations might not work. So in this case, I'm going to use x squared as my q and sine 10x dx as my dv. So in doing so, I'm going to have the derivative of 2x dx. Here, the integral of sine 10x dx, if you remember, would then become, if you let u be equal to 10x, du becomes 10 dx. So that becomes so we divide both sides by 10 and dx becomes 1 over 10 du. So in this case, if we're going to have sine 10x dx, the integral of that, integral of sine 10x dx becomes 1 over 10 integral of sine u dt, which actually becomes 1 times negative cosine of 10x. There you go. So this becomes, our u becomes negative 1 over 10 cosine 10x. There. I wish I would place a plus c here, but what we're looking at is actually b. So therefore, integral of x squared sine 10x dx here would equal to x squared times negative 1 over 10 cosine 10x, that's uv, minus the integral of b, that's negative 1 over 10 cosine 10x, times du, that's 2x dx. So in this specific case, let's rewrite stuff. So I'm going to have negative 1 over 10 x squared cosine 10x. In this case, I'm going to bring it out as positive 1/5. So this big, how do they become positive 1? That's negative 1 over 10 times 2, then the negative sign. Plus 1/5 integral of x cosine 10x dx. If it was just cosine 10x dx, maybe we could have easily performed this integral. But with the x beside it, we might have to a little bit more. So with that, we need to do again integration by parts here. Let's use red color just to indicate. So if we are to do again the integral of x cosine 10x dx by parts, let's follow what we had here. Let u be equal to x and dv be equal to cosine 10x dx. So du becomes dx. Well, v becomes, we're going to find the derivative of this. Let u be equal to 10x, and we're going to get v is equal to 10 dx. So this is again the reason why we get a 1/10 u is equal to dx. Thus, integral of cosine 10x dx becomes 1 over 10 integral of cosine u du, which is actually 1 over 10 sine u plus c. And u is, in this specific integration, is 10x. This becomes 1 over 10 sine 10x. 1 over 10 sine 10x. Hence, bringing it back to the main solution, we have negative 1 over 10 x squared cosine 10x plus 1/5 times the integral of this is which is uv, that's x times 1 over 10 sine 10x minus the integral of v. I will bring out already 1/10 outside to v, that's sine 10x dx. So there. So fixing stuff up, finalizing stuff up, we're going to have negative 1 over 10 x squared cosine 10x plus multiplying these, we're going to have 1 over 50 x sine 10x minus 1 over 10 times integral of sine 10x dx, which we actually solve, which is here, negative 1 over 10 cosine 10x. Then there's our plus. So that's enough easily for that. So finalizing everything now. Oops, I think I forgot something. Yeah. The 1/5 is both for this and for this. So there should also actually be, let's rewrite that. So again, there's supposed to be also a 1/5 times the negative 1/10, and then our derivative of then the 1/5, then the positive 1/10 first. So the 1/5 here, the 1/10 here. Yeah. Sorry, my bad. It's supposed to be a positive 1/5. Then there's a negative 1/10 here. This negative 1/10. Then another negative 1/10 cosine 10x. There you go. Sorry for the confusion. I hope we avoid that when we do calculations in the future. So therefore, finally, it's quite long. Integral of x squared sine 10x dx is equal to negative 1 over 10 x squared cosine 10x plus 1 over 50 x sine 10x. This becomes positive 1 over 500 cosine 10x plus. There you go. Let's take a look at another example of integration by parts. Pause the video and try to see if you'll be able to solve this one. Assuming that you have, and probably you might have noticed something wrong here. So let's first try. Again, the integral of u dv is equal to uv minus the integral of v du. Hence, we need to select our u and our dv and then later on du and v. So, like what we've been doing before, it looks like it's easier to select e raised to x dx as our dv and hence sine x as our u. The derivative of cosine x will simply be sine x will be cosine x dx, while the integral of e raised to x dx is equal to e raised to x. So, the integral of e raised to x sine x dx becomes, that's u times v, so I'm going to write it already as e raised to x sine x minus the integral of e raised to x cosine x dx v du. So, in this case, it looks like we have to perform by parts again. So, we'll separate this one out here. And following the pattern that we already have above, we're going to assign u to cosine x while dv to e raised to x dx. Hence, du becomes negative sine x dx, while v simply becomes e raised to x. Hence, going back to our main solution, this becomes e raised to x sine x minus, combining this, it becomes e raised to x cosine x minus the integral of e raised to x times negative sine x dx. So factoring out that negative, I'm going to have e raised to x sine x minus e raised to x cosine x plus the integral of e raised to x sine x dx. Now, if you might have noticed it yet, it's time to notice it now. Take a look that we actually got back to what we're actually looking for. Doing the second integration by parts returns to what we're solving. So does it mean, sir, that we don't have anything to evaluate? No. Since it turns out that integrating this by parts would just simply go on and on and on, so might as well perform some basic algebra on this one. How do we do that? Oops, sorry. First, I have to write this like this. So this becomes minus here, but this becomes a plus here. So therefore, I'm going to have e raised to x sine x minus e raised to x cosine x minus the integral of e raised to x sine x dx, which is similar to what we are actually solving. So if we're going to continue this, it will just go back here and then the process just keeps on going. So by algebraic, at this point already, we can actually transpose it here and add the two integrals together. So I'm going to have e raised to x sine x dx plus integral of e raised to x sine x dx, which is equal to e raised to x sine x minus e raised to x cosine x. Since the process will just continue, let's just take that one entire integral. So adding this to, I'm going to have 2 times the integral of e raised to x sine x dx is equal to e raised to x sine x minus e raised to x cosine x. Now we divide both sides by 2. So there. Hence, we're going to have the integral of e raised to x sine x dx is equal to, that over 2 works on both sides, so we can have 1/2 e raised to x sine x minus 1/2 e raised to x cosine x plus. So in this specific example, if you see that you're going to actually do the integration by parts indefinitely, might as well perform this simple algebra so that you don't need to do over and over again the integration. Now, for this last example, let's try to do integration by parts. But this time, the integration will be the data rather will be spent in a tabular method. So we know that the integral of the general form is integral of ut is equal to uv minus integral of v d. So we'll do the same thing. We'll need to assign what is u and dv, and then later I'll find du and v. Instead of computing for v and d instead, since it's the tabular method, we just need to actually find u and dv, and then work from there. So in this specific case, it looks like it's easier to work with u is equal to x squared and dv is equal to cosine x dx. Let's fix this piece. So for the u column, that's x squared. For the dv column, that's cosine x dx. So for the u column, we keep on finding the derivative, and for the dv column, we keep on integrating. So that's a technique. You form two columns, one column for u and one column for dv. For the u column, you keep on differentiating. For the dv column, you keep on integrating. So for the u column, we stop when we reach 0. So in this specific case, we have x squared, then 2x, then 2, then 0. So from here, we're going to have the derivative, the integral of cosine x, as we know, is equal to sine x. That becomes sine x. Well, we can work on with the dx. We can just remove the dx at this part. Then the integral of sine x, as we all know, is negative cosine x. So cosine x. And the integral of negative cosine x would become, if I'm not mistaken, negative sine x. Here you go. So from here, what we're now going to do is for a third column that we're going to have a third column wherein we have to indicate the signs. So the signs here. So it's alternating. The first row is positive, the second row is negative, positive, then negative. Then from here, we would have to multiply diagonally. So, the integral of x squared cosine x dx is actually equal to, this is our first term. That becomes x squared sine x. Then, since here it's negative, but we took it here, this is what we multiply, so that becomes minus 2x times negative cosine x. And then here it's plus here, but this is what we multiply, plus 2 times negative sine x. So simplifying this all together, the integral of x squared cosine x dx is equal to x squared sine x plus 2x cosine x minus 2 sine x plus c. And those examples are examples of performing integration by parts.